My name is Byungdu, and from Baobab AiBIO and Seongyun University. The title of my talk is Quantum Computing for New Drug Discovery. And many parts of my presentation biographs were prepared by Professor Kyungtae No, who is the CEO of Baobab AiBIO. This shows a workflow of drug discovery, and at first we need to obtain target protein. So we need to do target protein structure analysis, and then find binding pocket analysis to find binding place to our target. So this is like generating molecule, protein binding site, and drug fragments. This structure analysis is very important. And then we make a lot of customized potential drug candidates and make a library. And then from that library, we virtual screening by using computer, and typically ligand-based screening and structure-based screening. We get hit compounds. Hit means exhibits significant medicinal activity against the disease. And then do another kind of screening with in silico toxicity and pharmacokinetics and other physical properties. We get lead. Lead is a smaller set of better candidates. So before clinical and clinical studies, we need to do many steps to do drug discovery. So every step, the quantum computer can be used. And also a cryo-EM, which is a Baobab's very recent new machine, can do protein structure analysis very well. So our drug discovery strategy is to dramatically reduce the time and cost of small molecular and protein drug development by introducing cutting-edge innovative technologies such as quantum computing and cryo-EM. And through those technologies, we would like to do drug discovery with our own pipeline, as well as in collaboration with other companies or institutions, and would like to platform provide service. And these are the list of cutting-edge technologies, which are mechanics-based drug design tools, so quantum mechanics-based, and AI-based drug design tools, specifically generative models and deep learning, and structural determination of protein and protein drug complex using cryo-electron microscope, and QC algorithms for quantum computing to in silico drug design. And Baobab AiBIO and Bioinformatics and Molecular Design Research Center, which is in Yonsei University, are working very closely and has capability CADD platforms. CADD means computer-aided drug design, and QC CADD application and AI platforms and many drug design experts. This is a roadmap of quantum computing application for cryo-EM analysis. At first, we need to get target protein with sequence information and generate 2D electron scattering image with cryo-EM single particle analysis. And by using this cryo-EM machine, we get thousands of 2D scattering data. With this scattering data, we can make 3D electron density. And from 3D electron density, we can reconstruct 3D protein structures. And then by docking simulation with QM, we can determine ligand protein complex structure. So as you can see, there are three pictures, same pictures of quantum computer in three different places. The quantum computer can be used for each different process steps. So quantum computer can reduce the data processing time of cryo-EM significantly. So this is very important for us. And then quantum machine learning, you have already get a very good introduction from previous speaker, Professor Park. And the quantum machine learning are explored in all development stages of molecular design with desired properties. And quantum generative models are used for learning latent representations of molecules and generating large amount of drug candidates. I will explain in a little more details about this. And quantum generative models have the relative advantage to cover the entire distribution because of the intrinsically probabilistic nature. And among quantum generative models, we are especially interested in quantum generative adversarial networks. And deep generative models are used for various representation types of molecules, such as string-based, graph-based, and shape structure-based. So quantum computing can offer a unique advantage over classical computing for drug discovery by using quantum chemistry simulation as well as quantum machine learning. And also, the quantum hardware is getting improved. It is improving every day, like IBM is improving every day. So we can use, if we utilize a quantum computer, we can do our drug discovery more efficiently. And quantum GAN, which you have already heard from, again, Professor Park, it has a very strong expressive power in learning data distributions with much less parameters. So it can speed up learning and training, and it has the ability to search exponentially growing chemical space with increasing qubit count. And near-term quantum computers, which is still error-prone, like IBM quantum computers, are very useful for quantum GAN. And hybrid GAN model is used as already seen previous talk. The quantum computer and classical computer we can use together in hybrid fashion. Then the quantum GAN mechanism with the hybrid generator and classical discriminator can be done. And also, by using classical computer together, it requires fewer qubits, but still exploits the benefits of quantum computing. This shows schematic diagrams of two quantum computing paradigms. The first one is just using quantum computer, quantum circuit in its input state and quantum circuit, and at the end it has a measurement readout. This is a standard gate model quantum computing. But nowadays in near term, which has errors, as you have already seen this variation of quantum computing with the quantum part and classical computer together. So in quantum part, in this quantum circuit, there's a gate with parameters, and after the operation, gate operation and measurement, if it input to classical computer, then a classical computer does optimization and propose better parameter to quantum circuit, and it goes on. So until they have, for example, ground state energy of some molecular structure. So this variation of quantum computing is very important for near-term quantum computer. I will show one example how quantum computer is being used for drug discovery. This is a QGAN, as I mentioned, which shows a generator part and discriminator part. This is a generator try to make many synthetic molecules, and discriminate from real molecular distributions if it's the input molecule is real or fake. So it discriminates between these two, and generator would like to cheat so that it make this molecule as close as this real molecule, so discriminator cannot discern which one is real and which one is fake. So by training, at first train the generator make many molecules, and then discriminator trained for a while, and then generator train again and go back and forth until it make a very similar molecules. So this kind of things can be done in classical computer, but with quantum computer, it's this latent space. This is use some random noise, which is more efficient in quantum computer. So in this case, string-based, this one is a string, indicates some molecular strings, but sometimes use the graph-based, which is like example here. A node is atom, and this H is bond. So atom vector and bond matrix, we can use those and make this graph. As I mentioned, this generator is hybrid. So quantum part and classical part here, and discriminator in this case is used for as classical computer is used. So this shows a more detailed schematic of drug discovery process using quantum gain with hybrid generator. Here hybrid means, as I mentioned, this is a quantum part. This is a classical stage neural network. And then at the end of this circuit, it can generate atom vectors and bond matrices. And then from that information, we can reconstruct synthetic molecular graphs. And if it's, we can make as many as fake molecules. And real and fake is a discriminator. And we use, they use a metric of a Frechet distance, which is similarity between two distributions, and also drug properties, so that they can make many drug-like synthetic molecules. If we look at hybrid generator a little more detail, then as I mentioned, this is a quantum part, this is a classical part, and initialize at first all 0, and Ry and Rg rotation with the G1 and G2 angle. And then this is an entanglement part with Ry rotation, and this one shows control rotation Z in 2-qubit gates. So we can repeat this part L times, and this theta 1, theta 2, up to theta 2n minus 1 are parameters we need to optimize. And after the measurement, this is a vector. This feature vector is an input for classical stage. And then after the neural network, then we can find, we can generate new synthetic molecules. Okay. So in summary, I have shown one example of how drug discovery can be done by using quantum computer. And so this left side part is a de novo digital drug design platform. We hope to generate billions of molecules within 2 weeks, and screening about 1,000 hit molecules, and then about 10 molecule lead, and then experimental result and find the candidate. And we can, this kind of process is being done now by using classical computer machine learning. But we hope with quantum computer we can accelerate this process. And Baobab has this kind of capability, and KQC will have a very advanced quantum computer like 433 qubit IBM quantum computers. So we really hope can work together and produce very nice results. And business types, as I mentioned, we can do customized service according to customers' request and joint research for purpose of IP share and hit lead candidate development of our in-house pipeline. And thank you very much and congratulations again. Thank you.